Welcome back to the second part of the Transformer series. To quickly recap, we previously created a simple tokenizer class that breaks down the text into sentences and tokens, forming training sequences that we can feed into the transformer. Each token in a training sequence is represented by an index number defined in our vocabulary. Then each token is transformed into a vector of a specified embedding dimension. We can also reconstruct each sentence by mapping indices back to the tokens. In this part, we'll complete both the encoder and the decoder sections of the transformer. We start with the init method, where we pass in an instance of tokenizer and the number of hits as parameters. The number of hits specifies how many separate sets of attention keys, queries, and values we compute. Each mapping is designed to transform the input embeddings with shape of sequence length by embedding dimension into a shape of sequence length by head dimension. Here our head dimension is 64 for 4 heads. Consequently, the weight matrices should have a shape of embedding dimension by head dimension. And we create random variables for weights and biases in initiate weights with proper shape. I add E to differentiate between encoder and decoder parts. So first we have self-attention in both encoder and decoder, but in decoder we use masked attention. Let's go to our previous example. For this sentence, we matrix multiply the query by the key, and after applying softmax, each row in the resulting matrix shows how much each token pays attention to every other token. With softmax applied, the probabilities in each row sum to 1. In the decoder, we need the current token at each time step to only focuses on tokens from previous positions, not future ones. To enforce this, we use a mask. Before applying softmax, we set the scores of future tokens to a large negative number, which results in a near zero probabilities for these future positions after softmax. This ensures that at any given time step, a token doesn't see tokens ahead of it. To implement this, we create an upper triangular matrix using NumPy, setting elements above the main diagonal line to 1 and the rest to 0. We then multiply this matrix with our scores, only keeping scores above the diagonal. We multiply each element by a large negative number. Then we add this masked matrix to our initial scores. So when we apply softmax, values in the upper part of the matrix, which are future positions, become nearly 0. Additionally, we apply padding mask for padding tokens in the sequence so they don't dominate our model's predictions. We do this by checking the input sentence for indices equal to our padding, that is 2 in our example. Then generating the mask with a compatible shape to our input, and similar to future tokens masking, we apply this mask. And now, considering these settings, let's write a general self-attention mechanism that supports both the decoder and encoder. First, I create an attention list to store the output of each attention head. Then I set up both future and padding masks. To determine if we are in the decoder, we check the mask future tokens flag. If it is set, we apply mask self-attention in the decoder. I'll add this masked attention weight setup in our init weight method. Let's also create a helper method that accepts the input embeddings and weights, returning the key value and query matrices. We calculate the scores and perform masking for future tokens. Next, if we are in the encoder, we simply calculate the scores using the encoder weights. We then apply the padding mask to ensure that padding tokens don't affect the model's learning. We apply softmax and calculate the attention by a matrix multiplying the score by the value. We join the attention heads and combine the outputs from each head using wout mask for the decoder or wout e for the encoder. Adding the initial embeddings, we normalize to produce the final output. Next, we have cross attention in the decoder. Unlike self-attention, where queries, keys, and values all come from the same layer output, in cross attention, the keys and values come from the encoder output, while the queries come from the previous decoder block output. We use the encoder's output for cross attention because it provides useful context from the entire input sequence. This encoded output is rich with information about the input structure and meaning, which is crucial for generating accurate translation and predictions in tasks like machine translation or text generation. It is interesting to know that the authors make this intuition by comparing these tasks to what translators do. They keep going back and forth between the original text and the translation to pick up relevant parts of the input to create an accurate translation. To implement cross-attention, we write a method that also takes the encoder output as input. Here, keys and values are derived by matrix multiplying the encoder output with their respective weights, while queries come from the previous decoder block. We add weights of cross attention to init weights method. We follow the same steps to get an output of shape sequence length by embedding dimension. The remaining blocks are similar to those in the previous module. We have feed-forward layer with ReLU, activation, layer normalization, and a linear layer. Let's write an encoder method to include all the blocks in the encoder. We take the embedding vectors for each token in the training sequence, add positional embeddings, and then stack multiple layers of this architecture to get the final encoder output. I define num_stack to set the number of layers, compute the self-attention output without future token masking, and pass it through the first and second feed-forward layers. This network structure is repeated with updated inputs for each layer stack. Let's create an instance of the transformer with 4 heads. And a stack depth of 2 and encode a sample training sequence. The score matrix in self-attention will have a shape of number of heads by sequence length by sequence length. When we multiply this by the value matrix, we get an output of shape number of heads by sequence length but by head dimension. Next, we concatenate the outputs from each head so the final shape matches the original input shape. We repeat this for second stack and getting the final encoder output. Next, for the decoder, we start with the positional aware input embeddings. For each stack, we first calculate self-attention with future tokens masked, then perform cross-attention with the encoder's output as input, We pass this through a feed forward layer So let's add the weights. Applying layer normalization. This process is repeated according to the number of stacks. So we have a final output of shape sequence length by embedding dimension. To predict the most likely token at each time step, we need another transformation to map each row to a probability distribution over the entire vocabulary. To do this, we initialize another weight matrix with a shape of embedding dimension by vocab size. Multiplying the result by this matrix and applying softmax gives us an output of shape sequence length by vocab size, where each row shows the probability distribution for each token, identifying the most probable next token for each time step. Finally, let's decode a sample. First, we apply self-attention, followed by cross-attention, and then feed forward and normalization layers. Repeating these steps for the second stack, we transform the result to an output of shape sequence length by vocab size. By applying argmax to each row, we identify the highest probability token at each time step. During training, we pass the entire input sequence to the decoder at once. By applying a mask to prevent the decoder from seeing future tokens, it learns to predict each token at each time step simultaneously in a single forward pass. During inference, we begin with a small initial sequence of tokens. Typically start with the start of sequence token. We feed this sequence into the decoder, which then predicts the most probable next token. This predicted token is appended to the sequence, and the updated sequence is fed back into the decoder to predict the subsequent token. This process continues until reaching the desired sequence length or until the model generates an end of sequence token. In the encoder, during inference, the entire input sequence is passed at once and it generates context-aware embeddings for each token in the input. These embeddings are then used as a reference by the decoder in each step of generation to maintain coherence and relevance to the original input. So that's it for today's video. In the next part, we try to train our model using TensorFlow. Thank you for watching.